Hello, everyone. We are here and we are going to continue on our quest for thermochemistry knowledge. All right, we're starting section 5.2, and here's where we're going to get into a little bit of math. So have your calculator handy and let's go. All right, so have you ever wondered why sand on a beach is so much hotter than the water? Well, in case you haven't, it comes from, or the answer to this comes from a concept called specific heat capacity. And the variable for specific heat capacity is C. It's not H because I don't know why. Well, H is for something else. We'll get to that momentarily. But the variable is C. And what does the specific heat capacity stand for? Well, it's the amount or quantity of thermal energy, so the amount of heat needed to increase the temperature of 1 gram of a specific substance by 1 degree Celsius. So each substance has its own value, or how much energy it requires to heat it up, 1 degree Celsius. So because of that, let's take a look at this unit. It's joules, and that's the amount of thermal energy per gram degree Celsius, or per 1 gram per 1 degree Celsius. So let's take a look at this chart, because what you're going to see is that water has a pretty high specific heat capacity, and that has to do with all the intermolecular forces with water. As we all know, there's lots of hydrogen bonding and dipole, and there's the whole trifecta, as well as van der Waals and London forces and things like that. So if we take a look, this is one that we're going to actually be requiring for pretty much most of our calculations, because a lot of the assumptions we make, we assume that our solutions are similar enough to water to use this specific heat capacity of water. Okay? There's going to be a lot of assumptions in the math we do, and much like physics, the assumptions make the math easy, because if we didn't have them, we probably wouldn't be able to get an accurate reading. So you got to just go with the flow. Take everything with a grain of salt. Okay? So moving on, we're going to be talking about something called calorimetry, and this is kind of a big deal. In fact, first year you'll probably do a calorimetry lab, and had we not been in the situation we are in now, we would definitely be doing a calorimetry lab at school. And at school, because we're so high tech, we would be using something called a coffee cup calorimeter, which pretty much is 2 nested coffee cups, one on the bottom, one on the top. You cut it off so they can wedge into each other. And so that, and then you shove a thermometer in. So you, like, just to kind of go coffee cup, an inverted coffee cup. Okay, and you guys know I can't draw, but that's the way it would go, and there would be your thermometer, and you'd have a liquid in there, and your thermometer would hopefully hit to the liquid, or it wouldn't be measuring anything. But in any case, let's see what the heck calorimetry is. So we know metry means the measurement of something. Calorimetry is the measuring of the change in thermal energy. So think of what a calorie represents. It's a certain amount of energy, food energy associated with metabolism of the body. So calorimetry is the measuring of the changes of thermal energy in a chemical system. So don't forget what we talked about yesterday. A chemical system refers to reactants being changed to new products. Okay? And so we're going to be using this device called a calorimeter. Okay, so this one's a coffee cup calorimeter, and in this case, a lot of them are a lot more in the lab. They're a little more high tech. We don't have those. We would have used a coffee cup one. I don't know what you're going to use next year, but we'll see. Okay, so moving on. I'm going to scooch this up. Now comes the fun stuff. I love it. Calculations. So we're going to have some assumptions. Dun, dun, dun. These assumptions are if we're measuring heat transfer and physical or chemical changes. We are not, in the confines of SCH4U, going to be dealing with nuclear change. That's beyond my pay grade. That is definitely beyond your pay grade. So physical chemical changes that take place in water. So remember what I said earlier with the specific heat capacity. One of the main assumptions we use is that the solution that we're dealing with these calorimeters are dilute enough that we can assume they behave like water, or they have the density of water. Okay, so they take place in water, or they're sufficiently dilute that they are like water. Okay, so the assumptions: any thermal energy transferred from the calorimeter to the outside environment is negligible. So remember a word we use, well, actually it's two words. I'm just going to write this out. We are going to assume that our system is an isolated system. Okay, so nothing out, nothing in. Is that the case? No. We are making an assumption, especially if we're using styrofoam cup or coffee cup calorimeters. Are they isolated? No way, Jose, but guess what? It makes the math easy, so we're going to go with it. Next, any thermal energy absorbed by the calorimeter itself is negligible, meaning for our purposes, the styrofoam doesn't absorb any heat and it doesn't release any heat. So we want to assume that our calorimeter doesn't buffer the transfer of energy in any way. Okay, so that's the second assumption. And the third assumption is that all dilute aqueous solutions have the same density. So that's kind of like what I was talking about up here. We're assuming that the solution we're dealing with in our calorimeter is like water. So it's not going to be super concentrated. It's going to behave like water. It's going to have the density of water, which is 1 gram per mil, and it's going to have the specific heat capacity of water, which is 4.18 joules per gram degree Celsius. And those are values that normally I would have said you have to know on a test, but these days I guess you could always have them beside your LMS quizzes, okay? But these would be standard values that you need to know. So then, in calorimetry, the total amount of thermal energy absorbed or released by a chemical system is given by the symbol Q. Okay, so when we talk about Q depends on 3 things. The mass of the substance, so how much of the substance you're dealing with. Okay, because obviously if we're talking about a cup of water versus a bathtub of water versus a swimming pool of water, the cup of water is going to heat up faster because there's just less of it, right? Secondly, the specific heat capacity of the substance. But in these cases, for calorimetry purposes, for the most part, we're going to assume water. And lastly, the temperature change. And I'm going to put a formula here. Q equals MC delta T. Okay? And Q in this situation is the amount of thermal energy that is transferred, whether that's absorbed or released. So don't forget, the mass of my substance is measured in grams. My specific heat capacity is measured in joules per gram degree Celsius. And lastly, my temperature change is in degrees Celsius. Okay? And don't forget, I'm not trying to insult anybody, but delta T equals T2 minus T1, just in case you forgot. Okay, so tricks that sometimes happen in questions, you're given kilojoules. So if you're given kilojoules, you got to convert to joules. Okay, or you're given kilograms, convert to grams. All right, so just be mindful of your units. So secondly, moving on. The value of Q tells you a couple of things. The magnitude, so the actual number, tells you how much energy we're talking about here. And the sign tells you, is the energy being absorbed or is it being released? Okay, so if we have a chemical system, in this situation, we're going to consider the water, the surroundings, and my chemical system, my chemical reaction. Okay, and the insulation could be our styrofoam or whatever we want to say it. So if it's an exothermic reaction, meaning energy is transferred from the system to the water, Q is negative. So let's write this down here. Exo Q equals negative. If the system absorbs energy, Q is positive. So if it's endo, Q is equal to a positive number because it absorbed energy, meaning it gained the potential energy. Okay? So, and that's exactly what all these red words are saying. So if Q has a negative value, the system transfers thermal energy to the surroundings. Energy is released. Energy exits the system. Hence, exothermic. So since energy exits the system, my water in a calorimeter gets hotter. If Q is positive, that means my system, my chemical reaction, needed energy. It absorbed energy, and it got that energy from the surroundings. So since heat or thermal energy entered my chemical system, it came from the surroundings. So my surroundings donated the heat, if you will. So the water surrounding my chemical system got colder. Okay, so don't forget our law of conservation of energy. Q of the system plus Q of the surroundings equals 0. Or if we're going to just do the magic, over the equal sign thing, the Q of my system equals, now this is an important one, negative Q of the surroundings. They are equal and opposite in magnitude. Yeah? All right. Moving on to the math. Are you ready? Okay, I'm as ready as I'm going to be. Let's see if I don't bungle this up on my page. All right, so what would be the final temperature if 250.0 joules of heat were transferred to a 10.0 gram or to 10.0 grams of methanol initially at 20 degrees Celsius? So I just want to remind you of grade 11 stuff. This is my least significant digit, so my answer is going to end up being in 3 sig digs. Okay, so what have I been given? I have been given that Q equals 250 joules of heat. I've also been given that my mass of methanol is 10 grams. Okay. I've also been given that my initial temperature, so T1 equals 20 grams. Okay. So in this situation, we were also given in the chart the specific heat capacity of methanol. So we can't assume that this one's water because they're telling us it's methanol. We're not saying it's a dilute solution. So if we go back to the chart, and I'll let you swing forward and backwards. I don't want to make everybody dizzy, but I will tell you. So if you look it up from the table, it's 2.92 joules per gram per degree Celsius. Okay, so that's what I've been given. What are we looking for? Well, we're looking for the final temperature. So, okay. So what's my formula, you ask? Q equals MC delta T. So let's solve this bad boy. Okay, so Q equals MC delta T. I'm just going to write it up here again just to kind of keep it all in the same place. So my Q is 250 joules. My M is 10 grams. My specific heat capacity, okay, and my delta T, you know one part of the delta T, but you don't know it all, so that's what we're going to be solving for. Okay, so once we do the math, what did I forget? I forgot my equal signs. I thought that looked strange. Okay, so we will solve for delta T. Delta T equals 250 joules divided by 10 grams, 2.92 joules, gram degrees Celsius. And just because you know me, I love crossing this business off. All right, let's do it. Joules, joules, grams, grams, and 1 over degrees Celsius divided by the reciprocal equals degrees Celsius. So we know we haven't made a mistake in terms of manipulating our formula. So, and through the magic of me already having the answer solved, I will give you the delta T. Hold the phone. Let me just do it on my calculator because I don't have it done. All right, so 250 divided by 10 divided by 2.92. Okay, so my delta T is 8.56 degrees Celsius. Okay, so if I know that's my delta T, so delta T equals T2 minus T1. So T2 equals delta T plus T1. Do you see what I did there? T2 equals 20 degrees Celsius. Oh, and I don't have you people to correct me. Look at what I did there. That's better. Okay, 20 degrees Celsius plus 8.56 degrees Celsius. My T2 is equal to 28.56 degrees Celsius. Yahoo! Let's go to 3 sig digs. I will change my color just because I want to. All right, so therefore, T2 is 28.6 degrees Celsius. Woohoo! That's our final temperature. All right, I'm going to move it on up. Exemple 2. A student places 50 ml of liquid water at 21 degrees Celsius into a coffee cup calorimeter. She places a sample of gold at 100 degrees Celsius into the calorimeter. The final temperature of the water is 21.33 degrees Celsius. The density of the water is that. Let's calculate the quantity of thermal energy absorbed by the water. Okay, let's do it. So what do we know? We know my given. We know my volume of water is 50 mils. Okay. We know that my T1 is 21 degrees Celsius. We know that my T2 is 21.33 degrees Celsius. So what that tells me is my delta T is equal to 0.33 degrees Celsius, right? T2 minus T1. Okay. We know my density of agua is 1 gram per mil. We also know the specific heat capacity of water is 4.18 joules per gram degrees Celsius. Okay. We are going to assume at this stage that the mass of water is 50 grams, because don't forget, density of water is 1 gram per mil. Okay, so once we figure that out, what are we looking for? We are looking for Q, right? So Q equals MC delta T, and Q equals 50 grams times 4.18 grams per degree Celsius. I wonder if I wrote too big. Oh, maybe, let's see, 0.33 degrees Celsius. Oh, got it in, yay. All right, go to a different color. Bam! All right, so grams, Celsius. We're in joules when we actually do our mathematique. Let me do it so I can do it. One momento. Okay, clear. 50 times 4.18 times 0.33 equals I got 60. Oh, wait, I must have hit something wrong. Hold on, guys. Let me try this again. 50 times 4.18 times 0.33, which equals 68.97 joules. And we are going to how many sig digs? 3, because of this guy right here. So my Q equals 69.0 joules. That is the amount of thermal energy absorbed by the water. And as always, I'd like you to read section 5.2 in your textbook. And here's a little homework for you. You take care. I'm going to make another video of 5.2, but at this stage of the game, I would just like you to stop right here, do these questions first, and then we'll